So this event, it's kind of titled with a question, so I thought I'd ask some more questions during my talk. And I don't think I'm going to give you any solutions, more some ideas of where those solutions might be. So a messy solution to a messy problem. This is I won't expect you to read this, won't be examining later, but this is a Sankey diagram showing the energy flows in the United Kingdom at the moment. And if you go and look carefully at this diagram, you see energy is flowing from pretty much from left to right. So at the bottom, you have our petroleum going primarily into transport. You have things like natural gas going into power generation and an decreasing amount of coal also going into power. Now, what's interesting about this diagram is there's very little coupling at the moment between the transport sector and the power sector and the domestic heating sector. So those three sectors can be treated largely in isolation. They're not coupled. If we go into the future, and perhaps some of the ideas that we've seen of where we're going, those sectors are starting to become increasingly coupled, especially through deep electrification. And when we go down that sort of route, then we have to start thinking, when we look at a solution for one sector, we need to look at a high level how that is going to impact the sectors and the rest of the economy. And it's interesting, I was with some social scientists on Monday. When they start talking about those sorts of things, they talk about climate change being a messy problem. It's a difficult problem to solve. It's an interaction between technology, economics, society. You need to think about all those together if you're going to find a viable solution. So, well, I'm here to talk a little bit about engines. There were two challenges I think that we need to address if the internal combustion engine is going to have a place as part of the solution to the carbon challenge. Now, the first one is all about oxides and nitrogen emissions, the toxic emissions, the driver behind things like Dieselgate. Now, what I would say is we can solve that problem, and it's all down to chemistry. So what I have there is a picture of the thermite reaction. So that's iron and oxygen reacting at high temperature, and you will be producing oxides of nitrogen from that reaction process. The diagram on your right that's a bit of Brighton Pier. That's reacting quite slowly, probably over 100 years. And I'm not a chemist, but I don't think you're going to be producing any oxides of nitrogen emissions from that reaction. So if you can get control of the chemistry, you can get control of the emissions. And that's what we've been finding in the lab. So this is some data from one of our research engines. This is a split cycle engine. I think some people from Dolphin N2 who can tell you a lot more about that maybe over a glass of wine tonight. And the key thing is really on the bottom. So we've got a dotted line there that says SULEV. That's the super ultra low emissions. So that is the California NOx emissions. And you can imagine that in California, they're pretty aggressive on what sorts of levels of cleanliness you need to get from the vehicle exhaust. And we're kind of there, all right? So we can solve, with an internal combustion engine, the toxic emissions problem. But why bother? Well, I think Colin set the scene really nicely there. So if we go down the electrification route with commercial vehicles, a lot of the smart charging options that we have with passenger car that mean we can take a lot of the strain off the power grids just aren't available. These vehicles work really hard for long periods of time. So, the electrification route starts to look a little bit unattractive. But what about the carbon? What can we do about the carbon? Well, there are a lot of talk, especially in Germany, about electrofuels, about taking power, turning that through in a carbon neutral way into essentially a sustainable fossil-based fuel. There are biofuel options as well, where appropriate. Okay, we've got to be very, very careful. I know there's all the stuff in the press there that you can actually end up in a worse place if you don't do this intelligently. Now, what I want to talk about is something a bit different. I want to talk about recycled fuels. So where do these come from? So just introducing that concept to you. So I think if we're going to, if we go back to the big picture, where do we need to be if we're going to have a society that is not having a negative impact, or as little impact as we can on the planet? Then we need to move to a circular economy. We need to be minimising the amount of input we're getting into the system and minimising our impact as a society as a whole. And that's across all sectors. So this is a diagram I grabbed off the web. Colin doesn't like kilowatt hours and such like. I don't like this diagram because it breaks the first law of thermodynamics because there's no energy going in. Otherwise we have a perpetual motion machine. So we have raw materials and energy going in, and then we have this circle where we have goods being manufactured, processed, used, and then recycled. But there is a problem from that because inevitably we are going to release some emissions, typically things like methane from waste from this type of system. And methane's really bad. Methane's a lot worse than CO2 as an emission. So what we'd like to propose is actually if we can capture that and upcycle that methane. So if we can take that methane and turn that back into a fuel and feed that back into our system, then we will limit CO2, but we've now reduced by at least an order of magnitude the impact that will have on the planet. And what we end up is with a reduction in the energy input. That's only a good thing because energy is going to be scarce, it's going to be expensive in a future circular economy. And also reduce the greenhouse gas output. And actually, if our analysis is right, this actually becomes carbon negative. This actually starts to reduce, acts as a negative impact on this, well, a positive impact in reducing the carbon emissions. So where does this all come from? Well, the first is from the drainage system. So, we produce waste. We will always produce some form of waste, which will have to be disposed of. If you can capture the methane emissions from there, now we think this isn't currently accounted for in the carbon budget, so this is methane released into the atmosphere, is warming the planet, but isn't been accounted for. Then we think you can address about 5% of the current fuel needs in the commercial vehicle fleet. Now, what's more interesting is I cut my grass at the weekends. What do we do with it? Well, we kind of put it on the compost heap and it sits there releasing CO2. If we can capture that, right, you can produce enough potential fuel from that to power 40% of the fleet. So with a bit of intelligent logistics, a bit of upcycling of some waste, then we start to get to quite an interesting solution to the problem. So if we return to our messy complex system, so in a renewable economy, if we're looking at a truly sustainable system, then our energy is coming from the sun, unless it's nuclear where it's coming from somebody else's sun. And if we think about that, we've got solar panels, we've got wind generation, going into electrification, powering the passenger transport fleet, maybe producing some hydrogen. We're going to fuel cells, power things like buses and such like. But what also we could do is we could convert some of that energy into gas and then into a fuel, and then Audi have proposed some interesting concepts around that. We've got the biosource, and then we've got the other sources. So we've got waste from our domestic world, potentially from grass cuttings, and we can produce those into a sustainable fuel, then powering these kind of hard to electrify applications. Where we got vehicles, transport systems which are running for a long period of time, and real electrification becomes quite a difficult solution. So I think that's everything I've got to say.